work problem 2 on this back page 423, wherever it is, something like that. The luminous intensity in candelas. So this would be the luminous intensity up here. And the unit is candelas, which is a measure of brightness, of a lamp at varying voltage V. So voltage is along here. Is given by this function. 4 times 10 to the minus 4. Again, this 4 times 10 to the minus 4 is just a number. Moves the decimal point back 4 places, 0.304 is another way we could write it. So what I've done is, on autograph, I've plotted, instead of I, I've had to put into autograph y equals, because it only recognises x and y, 0.304, which is the 4 times 10 to the minus 4, x squared. So I plot that, and I've got this function that you're looking at now. So what that's saying is that for different voltages, we get different intensities. And it's not a linear function. As I increase the voltage, the intensity is going up as the square of the voltage. Determine the voltage at which the light is increasing at a rate of 0.6 candelas per volt. So, somewhere along here we can see that the gradient's increasing. So we're after the point at which it's increasing at 0.6 candelas per volt. So what we need to do is to differentiate it, let that differential equal 0.6 and work out what the voltage is at that intensity, at when it's increasing at that rate. Okay? So that's the idea of the problem. So we take our function and we can write it as I equals 0.0004 v squared and differentiate it. What notation do you use for the differential? Di by dv, yeah, divide. Don't say over, di by dv is the way we say it, although you're right. Okay. Another way I could have written this function is I, and then in a bracket put the other variable, which is v, and so then I would have written the differential as I prime v. Either way, okay. And so to differentiate, just bring the power down. 2 times 0.304 is 0.308 v. But then we're told that we want to find v when di by dv, or v prime, I prime v, equals 0.6 candelas per volt. So we form a little equation. 0.308 V equals 0.6. So just divide both sides by 0.308 and you get 0.6 over 0.1238, which comes out to be 750 volts. So if we look at here, well, we can see we're nowhere near 750 volts. So if we plotted this on autograph, we go back to autograph, and what we need to do now is zoom out. So we zoom out on the function, and we're after 750, so I just keep zooming out until I get on the x-axis 750. Let's move it across. So I can see 750 now on here, it's around here somewhere. So I now need to zoom out on the y-axis until it comes down. And there we are. So now I can see that at 750, for the pointer here it is, at 750 volts, That's the rate of change of the function at that point. It's 0.6. Okay, so it's not saying that the intensity is 0.6. The intensity is nearly 200 candelas, but the rate of change of voltage with intensity, or intensity with voltage rather, is 0.6 at that point. Right, James? So we can't confirm the gradient using autograph like that, unless on top of this we decided to plot the differential function. So I had another function now, y equals the differential function, which was 0.0008x, wasn't it? If I put that on, hit OK, now it gives me another function, and it tells me what the gradient function is. So if I zoom in on this part of the graph at 750, which is here, around about, whoops, missed it, 750 is over here somewhere, so let's just go across. 760, 750 is around here, there. What's this value? So let's zoom in on the y-axis, and so this just expands it out a bit, and we can see that at that point the rate of change is 0.6, so that does confirm it. Okay, so we can use autograph to confirm by plotting a differential function. Okay.